In this next lesson, we're going to continue in the autosampler theme where we left off last time. So we're going to continue to work on similar learning objectives here. There are really three components to think about when programming and operating automated samplers, because these three items determine how many, and when samples are taken. How many, and when samples are taken. These three items ultimately help determine the quality of your sampling process. Firstly, we need to consider when the autosampler kicks on and off. Generally, a minimum flow depth or flow rate threshold is set in the programming to kick the autosampler on. When flow exceeds that minimum criteria, sampling begins and continues as long as the flow remains above that threshold. The graphs show two hypothetical loads that would result from your data collection if you set the autosampler to start collecting samples at 1 cubic meter per second in the top graph or at 0.1 cubic meters per second in the bottom graph. The samples are collected at a 10-minute increment in both graphs, so the only difference is when the autosampler kicks on. You'll notice more samples are collected in the bottom graph, which provides better sampling coverage of the hydrograph because the autosampler in that case kicks on earlier and runs longer. This example quantifies the difference in resulting calculated load, where it's clear that the top autosampler example has missed some of the load. It's a good illustration that if you set your sampler to turn on too late, you risk missing an important part of the resulting load because you won't have those samples. The second criteria is the sampling interval. Two options, time-based or flow-based. Time-based sampling can be called a variety of names, but in short, this is where samples are taken based on time increments, such as every 30 minutes or every 4 days. Time-based sampling is simple because time intervals are easy to measure and document, and clock failures are rare. However, remember, an autosampler only has a set number of bottles. So if you set the time frequency too close, you'll end up with all your bottles filled and you might not have captured everything you wanted to capture. Or the other risk is that you could end up with way too many samples to analyze. The second kind of sampling is flow-based sampling, which is where samples are collected on flow increments such as every 200 gallons or every 3 millimeters of equivalent depth over your drainage area. Flow interval sampling requires continuous discharge measurement to sample once the sampling interval has occurred. In other words, flow interval sampling requires you to have an autosampler that directly communicates with your flow monitoring device so that the sampler knows when to sample. It's generally accepted that flow-based sampling is better than time-based sampling. That is, flow-based sampling provides less data uncertainty than time-based sampling. This is because a greater proportion of those flow-based samples are collected when you have higher flow rates. This example shows that time-based samples as x's, which you see are equally distributed across the x-axis, which is time. The flow-based samples are illustrated with squares, and you see they're not equally distributed with time, but those squares appear more frequently when the flow rate is higher. These higher flow rate periods correspond with times of higher nutrient transport just because there's more water leaving the field, so it could be important to sample more frequently during those times. My last note on time versus flow-based sampling, one nuance for my lab is that we often use Teledyne ISCO brand 3700 models, which are not able to communicate with a flow device, unlike the more expensive 6712 models. We use 3700s because they're roughly half the cost of 6712 models. So at many sites we do time-based rather than flow-based sampling, although we know that flow-based sampling is generally recognized as better. Also remember, from the previous module, you need to consider not just the cost, but also your team's expertise and training when designing a monitoring program. I have found that for people who haven't programmed autosamplers before, time-based sampling is much more straightforward to program. The last important consideration is if you take discrete or composite samples. Discrete sampling is where one sample is collected per bottle, typically over a couple seconds or about a minute into one bottle. These are snapshots in time. But remember, most autosamplers only hold a max of 24 bottles, which is where composite sampling provides some benefits. Composite sampling essentially increases autosampler capacity by collecting more than one sample aliquot into one given bottle before the autosampler moves on to the next bottle. An example would be collecting 100 milliliters every 6 hours, 4 times a day, to create one 400 milliliter composite daily sample. By putting multiple samples into one bottle, you lose some nuances of those individual samples, but nevertheless, composite sampling is recommended to control the number of total samples that you have to collect. An obvious question, especially if you are manually grab sampling, is how often should we collect samples? A study from Purdue University in 2003 found that there was a 92% probability of being within plus or minus 15% of the true nitrate loss, annual loss, for subsurface drainage if you sample weekly. And you can see the figure shows that for each of these 3 water years, the upper and lower bounds of being close to the true nitrate loss, annual nitrate loss, are much smaller for the 7-day sample frequency compared to the 30 or 90-day frequency. A more recent study recommended that samples be collected every 13 to 26 hours for dissolved reactive phosphorus and every 3-ish to 18-ish days for nitrate. Those findings written out on the slide include monitoring of small watersheds, but in the table, I pulled out their results for just their tile drainage outlets from this really great study. You see that as your acceptable uncertainty increases, so does your sampling frequency. That is, you don't have to sample as frequently if you're okay with a little more uncertainty in your estimation of the annual load or annual loss. And that makes sense intuitively. You'll also know that the sampling frequencies for nitrate tend to be much longer than they are for dissolved reactive phosphorus. That's because dissolved phosphorus tends to be much flashier and more storm flow driven than nitrate, so you really need to be sampling quite frequently if you want to have high certainty that you've captured the real true annual dissolved phosphorus loss. One last question is how much samples should be collected? The short answer is that you need enough for all the analyses you're going to perform on a given sample, plus enough to reanalyze samples if the sample needs to be reanalyzed, which you never know beforehand. Often for wastewater, you fill a separate sample bottle for each analyte that you're going to analyze for, which is a lot of bottles in some cases. But in tile drainage studies, we usually just collect one sample and divide it into aliquots, or smaller samples divided from the one sample when needed. The standard methods for water and wastewater recommends a 1 liter sample volume. We generally collect about 1 liter and then filter and then only keep about 100 milliliters for analysis to save on storage space. See you next time.